Gauss's law in magnetism. Before coming to this law, let us see the field lines due to a bar magnet, a current carrying solenoid, and an electric dipole. Look at this bar magnet. In case of bar magnet and solenoid, magnetic field lines are produced. And we know the magnetic field lines form closed loops. They enter at south polarity and leave out from the north polarity of the bar magnet. The field lines pass from north to south externally and south to north internally. Same is the case with solenoid carrying current. It acts like a bar magnet. The magnetic field lines enter at south polarity of the solenoid and field lines leave out at the north polarity of the solenoid. Here also magnetic field lines form closed loops. But in case of electric dipole, electric field lines are produced. And these electric field lines leave out from the positive charge. And they enter at negative charge. Here no closed loops are formed. Now let us consider closed surfaces. This is closed surface 1 and this is another closed surface 2 around the magnetic fields. Same way at the solenoid also, this is closed surface 1 and closed surface 2 here. And in electric field, same closed surface let us consider 1 and 2. Look at this magnetic fields. These closed surfaces do not enclose any charge here. Whereas in figure C, that is in electric dipole, it is obvious that for a closed surface represented by 1, the number of field lines leaving the surface is equal to number of lines entering in it. This is consistent with the fact that no net charge is enclosed by the surface. However, in the same figure, for closed surface 2, there is a net charge Q is enclosed by the surface. And hence there is a net outward flux. But the situation is different for magnetic fields which are continuous and form closed loops. In figure A and B, for both the closed surfaces 1 and 2, the number of magnetic field lines leaving the surface is balanced by the number of magnetic field lines entering it. The net magnetic flux is 0 for both the surfaces in figure A and B. This is true for any closed surface we take in the field area. Now let us come to Gauss theorem in magnetism. Look at this diagram. The parallel field lines represent uniform magnetic field B, represented by this vector. We consider a closed surface S which has surface area pointing in the direction N. If it is an irregular surface, we consider elementary segments. One such elementary segment of surface area delta S, for which N represents the area vector. And this area vector is making an angle theta with magnetic field B. Hence, the component of magnetic field along the area vector is B cos theta, or the magnetic flux through the elementary segment is represented by delta phi B, which is equal to B cos theta into delta S, which is B dot delta S. So what is the magnetic flux through the entire surface? That is represented by phi B, which is equal to summation of all delta phi B's. Summation of all the magnetic flux through the elementary segments delta S over the entire surface. Or phi B is equal to summation of B dot delta S. And we know the surface is not enclosing any charge, hence phi B equal to 0. So according to Gauss's law in magnetism, net flux through any closed surface. Net flux means net magnetic flux crossing any closed surface is equal to 0, or summation of B dot delta S equal to 0 if B is the magnetic field. Thank you.